I was running through the field, but then I fell and hurt my blank. What does it take to fill in this blank? Well, for one thing, we'll need to know grammar, but we'll also need to have an understanding of what running is, how it can lead to falling, and what usually happens when someone falls. I fell and hurt my knee makes sense. I fell and hurt my democracy makes less sense. One way to get a neural network to understand this distinction is to simply train it to fill in the blank. And we just saw why. Filling in the blank is not just about grammar. It's about a useful understanding of what has already happened. This realization led many researchers to a famous problem, the problem of language modeling. We're first going to touch on one of the earlier works to use neural networks for language modeling, published in 2003 by Yoshua Bengio and his co-authors, a Neural Probabilistic Language Model. The question was simple. Given a sequence of words, could a neural network predict the next word? And if a neural network is going to predict a word, it needs a set of words to choose from. This fixed set is called a vocabulary. And generally, the pieces of this vocabulary are called tokens, but in Bengio's model, tokens were words. So the model is not choosing from seemingly infinite language. It has a fixed vocabulary for tokens. And in Bengio's model, the architecture is like this. It looks at a fixed window of previous tokens, called a context window, converts those tokens into vectors, feeds those vectors into a neural network, and then predicts the next word. But we just completely skipped over this idea of turning words into vectors. 2 videos ago, in 1986, we talked about this idea of distributed representations. Concepts like field or fell could be represented by vector states, where the semantic information is encoded by the pattern of the vector, and therefore its position in vector space. And in that same work, we saw that these distributed representations of concepts are in principle learnable by neural networks. Bengio and his co-authors applied this idea directly to words. Each word maps to a learned vector, a distributed representation. Before the training process, these vectors are random and arbitrary, and don't encode much useful information. But we allow these to be adjusted during training. As we train the network, not only are the network parameters tuned for next word prediction, but also the vector parameters become tuned for next word prediction. And in practice, we end up with these semantically encoded vectors, where semantically similar words are close in vector space. These are typically called embeddings, and Bengio's work demonstrates that these are an emergent consequence of the next word prediction task. The model learns embeddings because encoding the semantic content of the words is useful for next word prediction. So each token is mapped to an embedding. These embeddings are fed into the neural network. But how does the network come up with a word? Well, instead of having the network choose just one word from the vocabulary, we have it pick a probability score for each word. So for example, when the model reaches the blank, it assigns probabilities to each token. Hurt could have a high probability, and landed would be kind of probable as well. And for each other token, we'd see a probability. For unfitting words, we'd see low probabilities. And to get the next word, we can use whatever rule we want to pick a word from this distribution. And now we understand language modeling a little bit better through Bengio's feed-forward neural architecture. It's important to note this is not like LSTMs, which we looked at in the last video, but this work gives us an incredibly strong idea. Neural architectures can be successful models of language by learning distributed representations for words and then predicting probability distributions for the next word. And this is extremely powerful. Once we can predict one word, we can predict a whole sequence of words. If we predict hurt, we can then again ask the model. The model predicts my. Now we ask again, what comes next? The model predicts knee. We can keep asking the model to predict words over and over again. This is called autoregression. A model generates a sequence of words by repeatedly using its own previous outputs as part of the next input. We're still dealing with an input-output machine, we just run a loop around it to predict a sequence. And this sequence can be an arbitrary length, since we can also just train the model to predict a special stop token when the sequence comes to a conclusion. So, Bengio took a plain feed-forward neural network, trained it to predict the next word, and wrapped an autoregressive loop around it. Now we have a way to generate an arbitrary sequence of language. And this seems to be an effective architecture for sequence generation tasks. Bengio's model is able to predict the next word from fixed size local content. But ultimately, intelligence requires more. Even for just language, the task isn't always just continuing generating a sequence. For example, translation. If the input is "I fell and hurt my knee," and we want to translate this to French, we could try to train Bengio's model so that it generates the translated sequence after the input sequence. So, for the input sequence, "I fell and hurt my knee," we train it to output this sequence autoregressively in French, and then stop afterwards. Seems like this would work, right? But this means the model has a lot more to learn during training. It has to be able to infer boundaries for where the source sequence, English, ends. It has to be able to learn how this boundary changes and interacts with the French words autoregressively predicted afterwards. And most notably, the model has to hold some representation of the input sequence, and also some representation of the output sequence, all at the same time. And the biggest limitation is the fixed context window. If we generate enough words, the source sentence might simply fall out of view of the context window. This architecture doesn't have any explicit mechanisms for separating these problems, understanding the source sentence, maintaining that understanding, and then generating a target sentence based on that source. Machine learning is powerful, but only when the architecture supports it. This reveals an entire different class of problem that translation falls in, mapping one input sequence to a target output sequence, each of arbitrary length. We refer to this as sequence to sequence, or sec to sec. And solving this class of problem requires two things generally. We have to understand the input sequence, and then we have to conditionally generate the output sequence based on that understanding. And instead of trying to have Bengio's architecture learn both of these during training, we can instead build an architecture that separates these two problems. In 2014, Ilya Sutskever and his co-authors did exactly this when they published sequence-to-sequence learning with neural networks. They treated this as two separate architectural problems, understanding the input sequence and then generating the output sequence. Let's start by thinking about just one problem we had earlier, the fixed context window. The source sequence could slip out of view of the model. If we want the output sequence to be different, but still depend on the input sequence, we need to make sure we don't lose the input. In other words, we have to persist some representation of the input. If we're translating "I fell and hurt my knee" into French, we need to hold on to the meaning of the English while we generate the French. We need a module that can read the sequence, token by token, and leave behind some useful representation of what it read. If you watched the last video in the series, you'll probably realize LSTMs are a natural solution to this problem. Because the whole point of an LSTM is to process information over time while maintaining an internal persistent representation. So what we can do is we can use an LSTM to read the input. "I fell and hurt my knee." And as the LSTM reads each token, its internal state changes. And when we get to the last token, knee, the LSTM should have some internal representation of the entire input sequence. If we take this representation and persist it, we'll have some understanding of the input sequence stored in a vector. It won't be a perfect understanding, but it'll be useful enough for what it is trained to do. And we'll get more into that later. So, this first part of the model solves a subproblem of translation, taking the source sequence and building a representation of it. This part is called the encoder, since it encodes information from the input sequence into a vector. And since that vector holds all of the context of the input, we call this vector the context vector, a vector that's been compressed into a learned representation, a representation that's not dictated by us, but the training objective. The model has to discover what information is worth storing. If preserving the sentence's tense helps translation, the encoder will be pushed to preserve tense in this representation. A quick side note, this is a common theme we've been seeing throughout the series. Learning is not just about memorizing inputs and outputs. Learning is about discovering useful representations. So, the encoder reads the input sequence and builds this useful representation, the context vector. But we still need to generate the output sequence. The part that generates the output is called the decoder, and we'll get into that right now. So, earlier in the video, we already saw a clear way to generate a sequence, with autoregression. The first thing we might think to do for the decoder is to pass the context vector into a feed-forward neural network, and then predict the first French word. Then feed that word back in, and predict the next one. But this brings us back to a problem we already had. We saw with Bengio, a feed-forward next token predictor has a fixed size input, a fixed context window. So, if the network wants to know what it has already generated, we have to give it some fixed number of previous target tokens. This could work in principle, but it recreates the problem of words slipping out of context, just on the output side of this new encoder-decoder architecture. So, the decoder is building a sentence by outputting tokens over time. It needs to track what it's already said, which is why an LSTM is natural here too. We've solved this problem before. If we use an LSTM to autoregressively generate the output sequence, the LSTM will keep track of and constantly update its recurrent internal state. So, the decoder's memory is distinct from the encoder's memory. The decoder can focus on representing the output sequence so far, while the source sequence influences its generation through the context vector. And that's pretty much the entirety of this sequence-to-sequence architecture. We saw that our original single network feed-forward language model struggled with tasks like translation, because it had to do two separate jobs simultaneously. Now with this new architecture, you might be thinking this seems like two different language models glued together, the encoder and the decoder. What we've actually built are two recurrent modules with different roles, an encoder that reads input and a decoder that writes output. Together, this behaves like a language model. And let's not skip this point. The context vector is what conditions the decoder's generation. The context vector initializes the decoder with information about the source sentence. Then, the decoder receives a special start token, predicts the first token, updates internal state, then we autoregressively continue until we predict a special end token. Now that we have the architecture, there's still one glaring open question. The decoder's generation is based on its input, which is the context vector and the last word generated. We've already touched on how language models like this can be trained at the beginning of the video, but this scenario is a little different. The decoder is influenced by the context vector, and the context vector is built by the encoder. So how does the encoder know what to store in the context vector? For example, with the task of translation, our training data would have labels for the translated version of the sentence, so what the decoder outputs. But we don't have labels for how the encoder is supposed to represent that sentence. And again, we come back to the power of machine learning. The encoder and decoder are trained not as two separate systems, but as one system. When there's a wrong prediction, error flows backwards through the decoder and gets propagated into the encoder. So during learning, the decoder tunes what gets generated. And at the same time, the encoder is learning how to help the decoder by providing a useful representation. And let's also note, if we train this encoder-decoder architecture on translation, we wouldn't expect it to be good at summarization. The encoder would have to learn how to represent information useful for the training objective, which is translation. This kind of training task pressures the encoder to preserve information needed to reproduce meaning in another language. Word choice, tense, syntax, structure, things like that. These are less useful for a task like summarization, where the semantic meaning is more relevant than any grammatical syntax. There's another problem with this architecture, but it's not really clear until we look deeper into training. The encoder reads the input sequence left to right, but the decoder needs to generate a new sequence entirely, starting from the beginning of the input. And from this point, the beginning of the input is very far away, back at the beginning of the sequence. So the decoder is going to have a hard time trying to remember that. And if the start of the output sequence is generated incorrectly, these errors are going to compound each time in the autoregressive loop, resulting in a poor output sequence. So, the authors do a little trick to help the decoder start strong. Instead of having the encoder read the input sequence left to right, they reverse it. So the input sequence is read backwards, right to left. This means the context vector has more emphasis on the beginning of the input sequence. This shortens the pathway between the start of the input sequence and the start of the output sequence. It allows training to more strongly communicate between the source sequence and the target sequence. The authors explicitly describe this as minimal time lag. So, let's wrap things up. Before this video, we started with neural networks as plain input-output machines. And we saw that we can layer machinery on top of these to create language models. With this, our original neural network has become more expressive. It can now express the semantics and structure of single sequences. The second architecture we looked at gave us a way to map a source sequence to an entirely new output sequence. This adds more machinery on top of the previous language model through the encoder-decoder architecture. And this architecture is expressive in a new way. Now we can also represent a relationship between two sequences. In the series, and in this video alone, we've traveled extremely far in the history of neural-based artificial intelligence. Language modeling actually came long before neural networks, in the early 1900s. For a long time, it was dominated by classical statistical methods. And even after Bengio's work in 2003, classical methods were still dominant. But this work laid the foundation for the modern paradigm. Words can be learned as vectors, and predicting language can force a model to discover representations useful for a task. And the most profound idea here is that the higher level tasks, like translation and summarization, rely on this foundation of next word prediction. We've seen that to predict language well, a model has to not just memorize words, but it has to genuinely build representations of semantic meaning. Predicting the next word relies on understanding the semantics and context of the situation, and ultimately is something about the real world. And the power of representations really needs to be emphasized here. We aren't just learning arbitrary word labels. We're learning semantically meaningful distributed representations. And in the case of the encoder-decoder architecture, we're learning a representation of one sequence that can be used to generate another sequence. But this brings up a serious bottleneck. If we revisit our encoder, we see it has to compress the entire input sequence into a single fixed representation. No matter how long the sentence is, or how dense the information is, the decoder still needs to rely on this single representation. Fundamentally, this is an expressive limitation. The single context vector can only hold so much information. This single representation becomes a bottleneck, ultimately capping the expressive power of the system. And throughout the series, we keep seeing the same pattern. Neural networks are powerful, but this depends on the architecture we give them. Distributed representations made concepts expressible as patterns in space. LSTMs made information expressible across time. Language modeling made a single sequence expressible. And this encoder-decoder architecture made the relationship between two sequences expressible. And I'm really emphasizing this idea of expressiveness, because ultimately this is what AI architecture is all about. AI is partly about getting machines to learn, but machines can't learn if they have no structure for expression, and the architecture of an intelligent system limits what kind of ideas are even possible to express. This includes the human brain. Somehow, the architecture of the human brain gives rise to the kind of representational and expressive power that we have as humans, at least compared to these machines. But it also makes you think about the limitations as well. It's very possible that there are more expressive architectures of intelligence out there, beyond the human brain. Architectures that could express ideas impossible for us to comprehend. This is what makes work in AI philosophically interesting as well. As we try to build systems that learn, we also explore what forms of intelligence are possible. Thanks for watching my video. Continuing the series, we're going to follow the paradigm of language modeling and find out how language models have been augmented, built on top of, and transformed into the incredibly powerful machines we use today.